on scalable computing and low precision floating point algorithms. Before we start, I would like to thank my two mentors, Dr. Savitska, my school mentor, and Sandeep Kurani, my industry students. So our outline for today, I'm going to first explain the motivation behind this research, then I'll explain the problem that we directly address in this research. I'll introduce the two algorithms that we use, and then I'll introduce our hypothesis for our experiments, and finally I'll share my results from these experiments. Energy demands have been predicted to exceed our national supply and double by 2030, as you can see from the chart on the right. And the reason for this is the increased use of AI training and inference. AI algorithms typically use full precision floating point arithmetic. And one way to reduce this energy is to use lower precision floating point formats, like FP8, which uses more than 10 times less energy. But by using these formats, we also need to account for the accuracy loss that comes with it. So our overall goal is to reduce computational energy while maintaining a reasonable accuracy. So our problem. Many scientific and engineering tasks require solving high-degree polynomials, 5th degree and beyond. And since these kinds of polynomials don't have a set formula, we will need to use iterative approximation algorithms, such as the Newton's method and the Ehrlich-Aberth method, which we will call the EA method. We want to use a combination of low-precision floating point formats while managing accuracy loss for these methods. So, and this sort of approach is also known as the mixed precision approach. So how can we strategically use mixed precision? So I mentioned like floating point before, but how are they actually represented in computers? So floating point data types consist of exponent bits, which define its dynamic range, and mantissa bits, which determine how precise the number actually is. So if we compare FP32 to FP8, for example, we see that since FP32 has 4 more bits, 4 more exponent bits, the maximum value is 10 to the 36 times greater, as you can see by these two values. And since it also has a lot more significant bits, the step, which is the maximum maximum error caused by rounding, is a lot less compared to FP8. So this is our first algorithm that we use in our experiments, Newton's method. Newton's method consists of 4 steps: calculating the polynomial, also known as the residual, calculating the derivative, calculating the delta, which is the polynomial divided by the derivative, and then updating our initial value by adding the delta to it. Since Newton's method is an iterative approximation algorithm, we need terminating conditions such that the iterations stop. And we use 2 terminating conditions. Either when the absolute value of the delta becomes smaller than a certain threshold, or when we reach a maximum number of iterations which we defined. Different levels of sensitivity are there for each step of Newton's method, so we hypothesized that we can use different floating point formats for each of these methods to reduce computational energy while maintaining a reasonable accuracy. Specifically, we defined that we can use a lower precision for the derivative because we believe the quantization errors can average out from iteration to iteration. And we believe we need to use a higher precision for the residual because this step directly determines when our iteration stops. So we want this number to be as precise as possible. So our experimental setup. To implement these methods, we use Intel's 8-bit floating point data type library and PyTorch's GPU implementation of FP16 and FP32. We use a Linux machine with an x86 CPU and an NVIDIA RTX 3070. We start with various initial guesses for all of the roots that are near 10% of the actual value, and this is because this is needed for Newton's method. We assumed in the study that the roots are representable in FP16, and all division calculations are done in FP32. So what we will do is we will test every combination of FP32, FP16, and FP8 for the 2 other steps of Newton's method. So what we did is we first chose these 6 roots, as you can see over here, and from these roots we created the polynomial above. the table on the right is a summarization of one root, which had an initial guess of minus 0.9, and then the final root being minus 1. The left-hand column in this table is all of the different combinations that we use for the polynomial and derivative calculations. And as you can see by the colors, we obtain 3 different kinds of solutions. Either we converge to the right root, we don't converge at all, or we converge to the wrong root in purple. But using our results from the convergence in the right root, we do see that we can use low precision for the derivative, and it still converges. Expanding this to all the roots for this polynomial, the initial guesses appear in the top left, and then our roots are in the top right. And then, as you can see from this, from the left-hand column, this is once again all the different combinations that we use. And these results still do confirm that using low precision for the derivative calculations are viable. But if we use low precision for the polynomial calculations, we see that we either get a lack of convergence or we get exceptionally high error. So you can see the average error and the count. So during our experiments, we ran across this interesting problem where we observed oscillations and a lack of convergence when using low precision. And this was due to the rounding implementation that we used, specifically NRE rounding. NRE, or nearest to round even, is literally what the name states. You round to the nearest number, but if your value is right in the middle, you just round to the even number. So for example, 2.55 will regularly round to 3, but 2.5 will round to 0, or not 0, it'll round to 2 instead of 3, as normal rounding usually goes. And what happens is that these intermediate values always round to the same values every single time, which does lead to oscillation. So instead, we implemented stochastic rounding. Stochastic rounding is rounding based on probabilities proportional to the relative distances between the 2 possible values. So once again, using 2.55 as an example, 2.55 would have a 55% chance to round to 3 and a 45% chance to round to 2. And what happens is this adds randomness to our quantized values, which does lead to more consistent convergence. So now we will see our results specifically for both energy savings and time savings. This big table on the right is a comparison of 2 different combinations. The baseline combination, where we use FP32 for every single step, and the other combination that we chose, where FP32 is used for the polynomial calculation, FP for the derivative calculation, and FP16 for the root update. And using relative latency based on NVIDIA's Hopper architecture, we find a 35% reduction in latency using this mixed precision approach. For energy estimation, using the energy consumption ratios provided by Mark Horowitz in this paper for FP16 and FP32, and then using extrapolation of those ratios for FP8, we find a 33% reduction in energy, despite a greater number of iterations. So, going back to this slide, one thing which I wanted to highlight was the results in purple, where we actually converge to different roots. This describes a limitation in the Newton's method, where depending on the starting value, you may not converge to the root that you were intending. And because of this, we wanted to implement another iterative approximation algorithm, specifically the Ehrlich-Aberth method, or EA method. The thing with the EA method is that all the roots are found simultaneously, and it contains a correction term, it contains a correction term, so all of the roots will converge to the unique roots, unless there are multiple roots. So if we compare these 2 methods over here, you see that they are pretty similar, but there are 2 key differences. Number 1, if you can see there's a V over here, this means all of the roots are stored in vectors, and this allows us to simultaneously calculate all of the roots. For the correction term, if you can see right here, which is different from the Newton's method, this correction term uses the information from all of the other roots to ensure that 2 initial values don't converge to the same root, unless once, as I stated before, you have multiple roots, which means you have multiple on the same root. So how does the EA method fare with this mixed precision approach? So what we find is the same pattern as before. The derivative in lower precision does work. However, if we compare FP16 for the derivative and FP8 for the derivative, with FP16, we get 6 iterations to converge all the roots, but with FP8, we get 17, which is a substantially greater amount of iterations. And because of this, we recommend using FP16 for the derivative for any implementations with the EA method. So after using the EA method and the Newton's method for the polynomial, we wanted to try this mixed precision approach for different kinds of equations, specifically a transcendental equation. So what we did is we used this mixed precision approach for the equation x cubed minus 3 cosine x. We calculated sine and cosine using the Taylor series with an approximation up to 8 terms. And what we found is after running this again, we see that our hypothesis still works. Using lower precision for the derivative and higher precision for polynomial calculations does result in a reasonable accuracy and lower energy costs. So now that we tried this for both polynomials and we tried this for transcendental equations, we wanted to apply this mixed precision approach for different kinds of roots or complex roots. So what we did is we tried once again this mixed precision approach for the Drude-Lorentz electron model, which is a polynomial of free and bounded electrons with both Drude and Lorentz terms, and where the roots are all complex roots. So the equation is listed here, and then these are all the roots. And after running both the Newton's method and the EA method, we find once again that lower precision for the derivative does result in accurate results, despite having a lower energy consumption. So our conclusion: we showed that a mixed precision floating point approach can significantly reduce computation and energy costs in numerical methods when finding the roots of high-degree equations. To find the roots of polynomials with multiple roots, we recommend using the EA method. We also proved our hypothesis of using lower precision for the derivative step while keeping the high precision of polynomial step does result in accurate results. When we have real roots, we recommend using FP8, and when we're using the EA method or complex roots, we recommend using FP16. We also found that stochastic rounding is necessary to find convergence, especially when using heavy quantization. In the future, we hope to test other floating point methods and other iterative approximation algorithms. So there's other floating point formats such as like FP4, and there's other iterative approximation algorithms which we hope to test with this. And we also hope to re-implement parts of our algorithms to make it more efficient, such as using the fast multiple method for the correction term in the EA method. Thank you for listening. Any questions?
Yeah, I have a question. So how do you know ahead of the time that the equation has real roots versus complex roots?
That was in our design. We chose so for the real roots one, we first chose the roots, and then we created the polynomial based on the roots. And then for the complex roots, we chose the Drude-Lorentz electron model specifically to test for the complex roots. So we chose our equation based, and we chose the roots based on what we wanted to test.
I see.
Any question?
Yeah.
What is the impact of application performance? Was it measured? Is the application performance is directly proportional to the energy used?
Yeah, I mean could you say that again? I think.
So I was asking the impact of application performance in different methods.
The application of what?
The computational performance.
Oh, the computation before. Sorry, I couldn't. I mean the bigger picture and the bigger application is that we're getting accurate results with lower energy consumption, and that is energy consumption, as I said in the first slide, is a big problem now. So if we can achieve reasonably accurate results while using significantly less energy, I mean, that is the key. That is the key impact. Yeah.
What was your biggest surprise during this project?
I think the biggest surprise was with like that oscillation problem that we had for a bunch of the combinations was like actually a pretty big problem that we had. And I did a bunch of research trying to figure out why this was happening. And when I found it, when it was actually the rounding implementation when we were quantizing values, I think that was like the biggest surprise. And like by just using a different rounding implementation, like a probabilistic rounding implementation, we found that led to greater convergence. So yeah.
All right, well, thank you again.